Okay, welcome to Lecture 32, Chapter 7, Section 6, Vesper, okay, VSEPR theory. Okay, so the Lewis structures is about structure. It lets us tell which atoms are connected to which and how they're connected. It tells us about non-bonding pairs and double bonds and things like that. Vesper is all about geometry. Okay? So that is to say, what is the actual shape of the molecule in 3 dimensions? So Vesper, VSEPR, stands for valence, shell, electron, pair, repulsion. Okay? So it's talking about electron pairs in the valence shell, and they're repelled by one another. Okay, so double bonds, non-bonding pairs, single bonds. Okay, so bonds, double bonds, triple bonds, and non-bonding pairs repel one another. Okay. You know, they're negative charges. They want to get as far away from one another as possible. That's it. Okay, it's a very simple sort of model. Okay, so what happens is you have all of these electrons, whether they're in bonds or in non-bonding pairs, gathered around an atom, and they are going to get as far away from one another as possible so as to minimize that repulsive force. Okay. So what this means is that we can use this to predict the geometry of molecules in 3 dimensions. And we can do fairly well with this. Vesper theory is a pretty darn good theory. But it involves a lot of memorization. And so study, study, study this weekend. So the way you work with Vesper theory is first you find the Lewis structure. Okay, once you have the Lewis structure, you can do the next 2 steps. Okay, the next 2 steps is first you find the electron domain. Well, let's actually write it out at least once. So electron domain geometry, and then you can get the actual molecular geometry. So we've already covered the Lewis structure. That was section 3, excuse me. So next we'll cover the electron domain geometry, then we'll cover molecular geometry. Okay? So the electron domain geometry is all about counting the number of electron domains. Okay. What is an electron domain? An electron domain is a region of space where electrons live. Okay, so a single bond, a double bond, a triple bond, or a non-bonding pair. Any one of these is one electron domain. So let's look at carbonite. Okay, CO2, 2 minus. 4 plus 2 times 6 plus 2 is 18 electrons. Carbon, oxygen, oxygen, 2, 4, 6, 8, 10, 12. So that's 16. 2 more go on carbon for 18. Carbon was not yet finished, so boom. All right. So now let's count. There. Now it's done. Now there's resonance, but that will play a role in geometry, but we can save that for a little bit later. So how many electron domains do we have on carbon? Okay. Well, it has a bond, a double bond, a single bond, I should say, a double bond, and a non-bonding pair. So non-bonding pair equals 1 electron domain. Our single bond is 1 electron domain. Our double bond is 1 electron domain. A double bond is only 1 electron domain. A triple bond is only 1 electron domain. More bonds, but all it's done is cram more electrons into the same space. Okay, so an electron domain is just a place where electrons live. Double bond, one domain. Triple bond, one domain. All right, so all told, the carbon has 3 electron domains. Whereas you look at carbon 8, CO3, 2 minus, C, double bond to O, single bond to O, O. This carbon has a single bond, a double bond, 3 electron domains. So these are going to have different geometries, molecular geometries, but they'll have the same electron domain geometry because they have the same number of electron domains. So electron domains, all you do is you count the number of domains, and the number of domains tells you what the electron domain geometry is. Then, once you know the electron domain geometry, you can figure out the molecular geometry. So, first let's look at 2 electron domains. Okay, so you have one thing with 2 electron domains. They get as far apart from one another as possible, which means they are going to be on opposite sides of this atom in the middle. Okay, that's it. Okay, it is a straight line. So, some of the things we can tell about this electron domain geometry. First off, this angle right here is 180 degrees. That's one of the things we need to know about molecules for reasons that aren't super important until much later. But it's 180 degrees because it's just, a straight line. Okay. We call this a linear molecule, or a linear compound, or a linear geometry. So some examples of this would be carbon dioxide and beryllium fluoride, which you may recall from the last lecture. These both have 2 electron domains, or I should say they each have 2 electron domains. So they are each linear compounds with a 180 degree bond angle. Now we have 3, not B, but 3 electron domains. Okay, they'd want to get as far apart from one another as possible. So we have our central atom, and then 3 things bonded to it. So let's just go B, 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 and there's our compound. And we call this trigonal planar. Okay, because it is a triangle on a flat plane. Okay, it's a perfectly flat molecule. So trigonal planar means that, we're talking, this is an adjective, okay? But, we say it has a trigonal planar geometry. And the internal bond angles here are 60 degrees. So a couple of examples of that would be boron trifluoride and good old carbonate. Okay, those are both trigonal planar compounds. They have 3 electron domains. They form this nice flat, perfectly, universally symmetrical, what have you, in equilateral triangle. It's a trigonal planar compound. Okay, and now 4 electron domains. For those of you who aren't good at thinking 3-dimensionally, I'm sorry. This is where we start going into 3 dimensions, because it is a tetrahedral geometry. That is to say, it does not form a square. Instead, it forms a tetrahedron, which looks like that. Okay. In order to get as far apart from one another as possible, they need to, take advantage of that 3rd dimension. Okay. So a tetrahedron, it's a 4-sided object. Okay, so here's the base, here's the back, let's call it K, then we have the left face and the right face. Okay, so it's a 4-sided pyramid. It is not, an Egyptian pyramid. Okay, is not an Egyptian pyramid. Okay, an Egyptian pyramid has a square base, for one thing. This is one of those regular solids, so all four faces are exactly the same. All the bond angles are the same. All the edges are the same. Okay. So, an example of this would be methane. It has four bonds, all nice and exactly the same. Okay. First things first, these things I'm drawing here. Okay, this triangular bond is coming out at you, and this dash bond back here is going back away from you. We needed to come up with some way to draw three-dimensional structures in 2 dimensions, and this is what we use. Okay, the triangle and the dashed line. Okay, another way to think of a tetrahedron, this isn't perfect, but it might help some of you. So here we have a cube. We have the carbon in the center of the cube, and then we have our hydrogens sort of catty-corner to one another. Okay. So that might be another way to help you think of a tetrahedron. This isn't perfect just because the bond angles aren't right. Speaking of bond angles, 109.5 degrees. It's not exactly 109.5. We're rounding just to get to that. But that is a good estimate. And it's well rounded. 109.5 degrees is the internal bond angle for a tetrahedral geometry. So other examples of tetrahedral geometry are ammonia and water. Okay. Ammonia, just to sketch it out really quick, has 4 electron domains, and water also has 4 electron domains. Notice that some of those electron domains are non-bonding pairs. That's perfectly fine. If you have a non-bonding pair, will still count as an electron domain. So all of those have 4 electron domains. They all have tetrahedral electron domain geometry. Now, 5 electron domains. Now, 5 electron domains is slightly different. First off, the name is called trigonal bipyramidal. Okay. So what it is you have the central atom with a thing coming up and below, and then you have a triangle coming out on the in the middle of it. Okay. So and that's why it's called trigonal bipyramidal, because you can draw it as two triangular pyramids stacked butt to butt. All right. Those two triangular pyramids, they're not tetrahedra. Okay, so that's why it's called trigonal bipyramidal, and not something with tetrahedron. Those are not tetrahedra, so it doesn't have tetrahedron in the name. It's trigonal bipyramidal. Okay, so 2 trigonal pyramids. Okay. The other thing is that unlike every other geometry, 5 electron domains gives it a different sort of geometry. It has 2 different positions. Okay, so it has the polar and the equatorial. Okay, sorry, polar or axial. Okay, it's not axial, but axial. Okay, so for the geometries we've seen before, all of the points, all of the places around them are exactly the same. They're exactly identical. All the bond angles inside are the same. That's not the case for this guy. Okay, the poles, the north and south pole, are different from the 3 equatorial atoms. Okay, so here we have a 90-degree angle, but here and here it's 120 degrees. Okay, that'll make a difference later on when we start looking at molecular geometries. And finally, our last electron domain geometry is 6 electron domains, and it is octahedral. Okay, that's where you have the central atom, Let's see. Okay, and then you have 6 things bound to it. So 1 up, 1 down, 1 left, 1 right, 1 forward, 1 back is another way to think about that. You know, the center of a 3-dimensional axis forms an octahedron. You know, you have your atom at the middle here, and then you have 1, 2, 3, 4, 5, and 6, okay, pointing out as far away from one another as they can get. Okay, so that's also an octahedral geometry. We call it an octahedron because when you draw it out, what you get is something like this. Oops, that's... Okay. Might be kind of hard to see, but that is an octahedron. Okay, what it is it's 2 square pyramids butt to butt. Okay, so this is over here where, you know, this is the top view. Okay, we're looking down on it from above. Okay, so here is an eyeball looking down on it from above. Okay, so here's the top atom in the middle. Then we have, you know, the 4 atoms at the corners of the pyramid. And then exactly opposite this top atom, you have the bottom atom. Okay, so that's another way of thinking of an octahedral geometry. Okay. Now, with an octahedral geometry, we've gotten back to a nice, highly symmetrical sort of figure, and these bonds are all 90 degrees apart. Okay, they're all exactly the same. So an example of this would be sulfur sulfur hexafluoride. Okay, that has a nice octahedral geometry. Okay, so those are the 5 electron domain geometries. So number of electron domains, electron domain geometry. Okay, so 2, 3, 4, 5, and 6. Linear, trigonal, planar, tetrahedral, trigonal bipyramidal, or trig-bipi, and octahedral. Okay. So now we're going to fill in this last column. Well, there's going to be 2 more columns for molecular geometry. So moving from electron domain geometry to molecular geometry, you have to think about non-bonding pairs. So in molecular geometry, you have to know number of electron domains and number of non-bonding pairs. Because the thing is, when you look at the molecule, you see atoms and bonds. In BP, non-bonding pairs are invisible. Okay? Whenever we look at these molecules, we don't see the non-bonding pairs. They disappear. Okay? So what you do is you draw out, you draw the electron domain geometry, then erase non-bonding pairs. For example, so let's look at 3 electron domains with 0 NBP, so with 0 non-bonding pairs. That would be something like boron trifluoride. Boron, fluorine, fluorine, fluorine. But you can also have a molecule with 1 non-bonding pair. So, for example, carbonite, CO2, 2 minus. Okay. Carbon, oxygen, oxygen, non-bonding pair. All right. So this has, has a trigonal planar electron domain geometry. But we can't see that non-bonding pair. It's invisible. So when we look at it, all we see is oxygen, carbon, carbon, oxygen. We can't see the non-bonding pair. All we see is a bent molecule. And that is what we call it. We call it bent. Because sometimes we're not fancy. So those are the two possibilities for when you have 3 electron domains. Okay? You can have 0 non-bonding pairs, in which case it is trigonal planar. Or you can have 1 non-bonding pair, in which case it is bent. All right, so I'll hurry through the others a little bit faster. Okay, so 4 electron domains. 0 is tetrahedral. Looks like that. 1 non-bonding pair is going to look like this. Okay, the top one has been removed. That was one of the 4 of the tetrahedral. So now what you see sort of a trigonal pyramid. Okay? It is not tetrahedral, even though it has a triangular base. It's like you've squashed a tetrahedron. Okay? So what we call that is trigonal pyramidal. Okay? It is a trigonal pyramid. Okay? And finally, you can have 2 non-bonding pairs. Okay, so now it's just bing, bing. You've eliminated 2 of the sticks off the tetrahedron, and it is just a, it's exactly what it looks like. It's a bent molecule. Now let's go to 5 electron domains. Now 5 electron domains, you might remember, is trigonal bipyramidal, trig-bippy. Okay. And that's the one that has 3 things coming out of the equator and then 1 up and down on the axis. And of course, that also means that you have 2 possibilities. Okay. When you put a non-bonding pair on there, is it going to go polar or is it going to go equatorial? Okay. Now, this is where I tell you non-bonding pairs are big. Okay? They take up more space than bonds. Okay? They're naked electrons. Okay? They don't spend any time near a nucleus, so there's no sort of shielding. There's nothing to counteract them. Okay? So because of that, non-bonding pairs take up a lot more space. So non-bonding pairs absolutely have to get as far away from everything else as possible. And so non-bonding pairs go equatorial. Okay. Non-bonding pairs go on the center 3, not on the poles. Okay. If they went polar, if it was polar, the non-bonding pair would be, like this, and it would look around itself, and it would see 3 things 90 degrees away. Whereas, if you put it equatorial, like this, it looks around itself, it sees 90 degrees top, 90 degrees on the bottom, and then these 2 guys at 120 degrees. And so, what we know is that 2 at 120 degrees is less than 1 at 90 degrees. Okay. So you get less repulsion if you put the non-bonding pair on the equator. Okay. If you put it on the poles, then it sees 3 guys at 90 degrees. It's very close. It's unhappy. You put it on the equator, it's going to see 2 at 90 degrees. Not great. But it's also going to see 2 at 120 degrees. Those 2 at 120 degrees is better than the extra 1 it would have gotten at 90 degrees. Okay, so non-bonding pairs always go on the equator. They go around the middle, not on the top and the bottom. So let's go ahead. Here's our first one. And this structure is known as bisphenoidal or seesaw. I really like the word bisphenoidal, but I can understand if you can't spell it. So seesaw is also okay. And that's because it looks like this. Okay. You've removed one of the three around the equator. If you were to turn that on its side, it looks like a teeter-totter or a seesaw. Okay. But the technical name, and thus the better name, is bisphenoidal. Okay. You can remove another one on the middle, replace it with a non-bonding pair, and what that gives you is what's known as a T-shaped molecule, because you removed two, and now you have the letter T. It goes T, because it's T. And finally, you can remove all three around the equator, and you get a linear molecule. It's just a straight line. And now, last but certainly not least, the last electron domain geometry is octahedral. With 6 electron domains, 0 non-bonding pairs gives us an octahedral geometry. So boom, boom, boom. All right. Now, because they're all the same, the first non-bonding pair can go anywhere. And it's going to, it'll never make a difference. It'll always give you the same geometry. So that is going to be what's known as square pyramidal. Okay? You remove one of them, and what that leaves you with is a square pyramid. Now, this is an Egyptian pyramid. Okay? It's got that square base. All right. So square pyramidal. Now, the second one, it does make a difference where you put it. The second one goes on the opposite side from the first. Okay? You want to get the non-bonding pairs as far apart from one another as possible. Okay, so when you put the first one on there, that breaks the symmetry of the octahedron. So the second one just goes on the opposite side from that. And that means it's going to give you square planar. Okay, it's just a flat square. So nice and simple. Okay, 4 sides, all equal length, and so on. The third one, okay, can't help it. It's going to give you a different sort of T-shape. Okay, we are slowly running out of places to put these non-bonding pairs. And the last one, if you put on 4, that's going to give you another linear molecule, just a straight line. The molecule with an atom in the middle. So those are the 5 possibilities for a 6 electron domain geometry molecule. So that is a lot of shapes. Okay. Fortunately, they're all based on 5 shapes. And one of those 5 shapes cannot have non-bonding pairs. Okay. So really, they're based on 4 shapes. Okay. So here is a chart. This shows you, some basic pictures, and you have the number of electron pairs available on the top or on the left-hand axis. The top axis there shows you the number of lone pairs or non-bonding pairs. So it starts with the 5 basic geometries, where you have 0 lone pairs: linear, trig planar, tetrahedral, trig bipi, and octahedral. And then it just gives you the increasing number of lone pairs. So 1 lone pair gives you a bent geometry, or trigonal pyramidal, or bisphenoidal, or square pyramid. Okay? Square pyramidal. Okay? You'll notice that a linear molecule can only have 0 lone pairs. Why is that? Well, look at what happens when you replace one of those 2 atoms with a lone pair, or a non-bonding pair. You just have 2 things bound together. 2 points is a straight line. It can't be anything other than linear. So that's why they have the cutoff where they do, why half of this chart is blank. Okay, so 2 lone pairs will get you a bent molecule for 4 electron domains. It'd give you a T-shape at 5. It'll give you square planar for 6. 3 lone pairs gives you a linear structure for 5 and T-shaped for 6. And finally, 4 lone pairs. That can only happen if you have 6 electron domains, and that gives you a linear molecule. Okay, so those are the shapes, those are the structures. You'll notice that it also has bond angles in there. Okay? And some of them have less than signs. So let's go back. There is a reason for that. Remember how I said non-bonding pairs? Non-bonding pairs or lone pairs are big. Okay? They take up more space, which means they squish other atoms together. Okay, so they're going to squish the bond. Okay, so like here we have some random trigonal planar molecule with 120 degree bond angles in there. You replace one of the atoms with a non-bonding pair. Okay, so that invisible non-bonding pair up there is, pushing down on those two bonds, forcing them together. So this bond here is a little bit less than 120 degrees. Now, how much less? That depends on the bonds. Okay, it's hard to really predict exactly what that is. So what we do is we just write less than 120 degrees. We're acknowledging that it's kind of squished. Okay? So you get that with all of your compounds. Okay? So for example, looking at, methane, ammonia, and H2O. Okay? They're all, they got electron domain geometry that is tetrahedral because they all have 4 electron domains. Okay? So here's methane. Here's ammonia. And here is water. Okay. And so because of that, they have different molecular geometries because they have different numbers of non-bonding pairs. So this is still tetrahedral up here for methane, but it's trigonal pyramidal for ammonia and just bent for water. And the bond angles also change. Okay, so methane is a nice, perfect tetrahedron at 109.5 degrees. But that non-bonding pair on ammonia squishes those 3 nitrogen-hydrogen bonds, that squishes them together. So it is 107 degrees. These are well characterized, so we know those bond angles. And then water. Water has 2 non-bonding pairs, so they really, really squish, and it is down to 104.5 degrees. So big squish, big old squish. So non-bonding pairs always take up more space. So remember that for your molecular geometry. That, for example, if it's 5 and 1, 5 electron domains, 1 non-bonding pair, that means it looks like this. Okay? But this is not a straight line, okay? Because those bonds have been squished as well. So really, the teeter-totter is slightly broken. I'm exaggerating it here so that you can actually see it. But, that bond is less than 90 degrees, and this bond is less than 120 degrees. That is less than 90 degrees. Okay? It's all a little bit squished because of that non-bonding pair. Similarly, for 6 and 1, the square pyramid, okay, it should look like that. It should all be 90 degrees, but, the non-bonding pair on the bottom squishes everything upward. Now, there are so many. It's 1 non-bonding pair versus 5 bonds, so it's not a big squish, but it is going to squish them slightly, so they're going to end up a little bit less than 90 degrees. So they're going to end up a little bit less than 90 degrees. It's not a huge change, but it's noticeable. Now, the thing is, when you get a lot of non-bonding pairs around something, you can sort of eliminate that squishing, or you can have a perfectly balanced squish. So like 5 and 3, okay, you have 3 non-bonding pairs, but they're all around the axis. You have a linear molecule. Okay, the 3 non-bonding pairs are squishing, yes, but they've perfectly counterbalanced it, so this is a 180-degree bond angle. Okay, similarly, 6 and 2, the octahedron goes down to square planar. You have 1 non-bonding pair above, 1 non-bonding pair below. They're squishing, cancels each other out, so you end up with a nice flat square planar molecule with 90-degree bonds. Okay, 6 and 3, that T shape, it's very squished. Okay, so less than 90 degrees. And finally, 6 and 4, well, you're back to a linear molecule again, where you have 4 non-bonding pairs circling around the outside. It's 180 degrees. The squishing all sort of counteract one another. Okay. So that gets you a fairly big, complicated chart. This chart puts it all into, sort of a single box, where you have the number of electron domains versus the number of non-bonding pairs. And then you just write the bond angle inside that, inside the picture there. Okay. So I suggest you memorize this chart or something very much like it. Now that we've gone over all the geometries, let's talk about double bonds. Okay, double bonds, they take up more space. They are bigger than single bonds. Okay, you should expect that. Okay, a double bond has more electrons crammed in there, so it's going to have more repulsion. Okay, more space than a single bond. Okay, but they take up less space than a non-bonding pair. Okay, so a double bond is bigger than a single bond. It is smaller than a non-bonding pair. And what that means is that you can look at molecules that have, double bonds in them. Okay, so for example, here is formaldehyde. It's carbon, singly bound to 2 hydrogens, double bonded to an oxygen. Okay, so this double bond here is bigger than the 2 single bonds. Okay, it takes up more space. It's squishing the 2 hydrogens together. So that means that this bond is, bigger than 120 degrees. This bond over here is also bigger than 120 degrees. And this bond down here is less than 120 degrees. Now, because a double bond isn't as much bigger as a non-bonding pair, it takes up more space, but it doesn't take up as much more space. Okay. So these are like 120.5, 120.5, 119. Okay. It's enough to change the geometry, but it's not as huge a difference as you would get with non-bonding pairs. Next up, extended geometries. Okay, if we could only look at single center molecules, like we've been looking at, this wouldn't do a heck of a lot of good for us. Okay? But what we can do is we can look at extended geometries, like C4H10 or butane. So C4H10 is carbon, 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 boom, 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 hydrogen, 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 hydrogen. Okay. So what is the geometry of this thing? It's butane. Okay, we don't really have a name for it. First off, because it's a big it's a slightly bigger molecule. Second, because, these things aren't really fixed, okay, in the way that you can think of them as with a single center. The molecule will wiggle and flop around, and it can twist and bend and so on. So it doesn't really have that same fixed geometry in quite the same way. But what we can do is we can look at individual carbon atoms and talk about their geometries. So let's go ahead and look at this guy right here, number 3 in the chain. Okay, carbon, it's got a hydrogen above, it's got a hydrogen below, it's also got that carbon there, and this carbon over here. Okay, so it's still got a tetrahedral geometry. Okay, it's just that 2 legs of the tetrahedron happen to lead off to a longer chain. Okay, so we have carbon 1, carbon 2, carbon 3, and carbon 4. You see, each one of those carbon atoms has a tetrahedral geometry. We can look at all of the atoms like this. Like we can look at the first carbon in the chain. Now it has hydrogen, 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 and then CH2, CH2, CH3, the rest of the chain there. So the whole molecule, okay, every single carbon atom on it, has that tetrahedral geometry. So if you were to look at it from the side, you would see carbon, bound to carbon, bound to carbon, bound to carbon. Okay, with each of them having, a tetrahedral geometry, giving it this sort of like an inchworm sort of appearance, a zigzag appearance. Okay. So that is what butane, sort of really looks like, a lot of the time, is that sort of zigzaggy chain. All of those organic molecules do that. And now, finally, let's look at polarity. So we talked about polar bonds. Now we're going to talk about molecules. Okay, so from bonds to molecules through geometry. Okay. So we need to consider geometry in order to know whether or not a molecule is polar or nonpolar. Okay. Because you can get a sort of flowchart. Okay. Does a molecule have polar bonds? So if the answer is no, then the molecule is non-polar. If the answer is yes, well, it could be polar or it could be non-polar. Okay. So let's say, is it highly symmetrical? If the answer is yes, then it is non-polar. If the answer is no, then you get a polar molecule. Okay? So in order for it to be polar, it has to have polar bonds and broken symmetry. It has to have both of those in order for it to be a polar molecule. Okay? So let me show you. Here is carbon dioxide. Carbon is bound to oxygen here. Oxygen is more electronegative than carbon. So that means that each carbon is going to have a negative partial charge, and carbon is going to have a positive partial charge. So each of those bonds is polar. You have a polar bond pointing to the right, and you have a polar bond pointing to the left. But those two bonds cancel each other out. It's like a perfectly balanced tug of war. Okay? So the pull to the left is exactly the same as the pull to the right. So you get polar bonds, non-polar molecule. Because those two polar bonds cancel each other out. Whereas you look at, say, water. Water has that bent geometry. So oxygen has a partial negative charge. The two hydrogens each have a partial positive charge. And now the two bonds can no longer cancel each other out. they're not exactly opposite one another. So the overall molecule has a dipole moment, a polar molecule, because the symmetry has been broken. The two hydrogens are both on one side of the oxygen. They're not exactly opposite one another. So that's how you determine whether a molecule is polar or not. Is you look for broken symmetry. Okay, so electron domains 2, 3, 4, 5, 6, and then non-bonding pairs 0, 1, 2, 3, 4. So I'm not necessarily going to draw every geometry because I don't have a whole lot of space. But, this one is going to be, it's linear, so it is non-polar, because the two bonds cancel each other out. So this I should specify if all bonds are the same. Okay? So if all the bonds are all the same, then that's what you're going to get, a nonpolar molecule. If you have different kinds of bonds, you might as well just give up and call it polar. Okay, so bonds are all the same, then just going right down the left-hand side, they're all nonpolar. Okay, because there's no broken symmetry. Okay, 0 non-bonding pairs means you have a highly symmetrical molecule. That does not mean that the rest of them are all polar. No. Okay, but this one is bent, so it is polar. This one is trigonal pyramidal, it's also polar. And then you have 4 and 2, bent is polar. Okay, here we have bisphenoidal, that's going to be polar. T-shaped is going to be polar. And then linear is nonpolar. Okay, you add that third non-bonding pair, and all of a sudden it becomes highly symmetrical again. These two bonds would cancel each other out. However, whatever the direction of those polar arrows is. Here we have a square pyramid. That's going to be polar. Then we have square planar is going to be nonpolar. Then we're going to get T-shaped, which is going to be polar. And then we're just going to get linear is nonpolar. So it's not necessarily the case that adding non-bonding pairs makes things polar. A lot of the time it does, but as you can see, 1, 2, 3 different molecular geometries with non-bonding pairs are nonpolar. Now, nonpolar versus polar makes a big difference. It is a huge deal in terms of how molecules interact with one another. I mean, oil and water don't mix. That's because oil is a big nonpolar molecule and water is a small, highly polar molecule. Okay? Polar and nonpolar, they tend not to mix. And that is just one of many ways that polar versus nonpolar can have a big impact on chemicals, chemical reactions, physical properties, and things like that. So remembering polar versus nonpolar, or being able to figure out however you have to do it. Okay, whether you memorize this chart or work it out so that you can, just draw this chart by figuring it out every time over and over again, whatever you have to do. Okay, make it so that you can figure out whether a molecule is polar or nonpolar. And practice, 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 practice is super important for this. Now, like I said, this is if the bonds are all the same. If the bonds are different, then you're going to have a polar molecule. So CH4, just carbon bound to 4 hydrogens. Okay, that is a non-polar molecule. CH3Cl, chloromethane. Okay, CCl, HHH. Okay, you see that carbon-chlorine bond? That's broken the symmetry of the molecule. Now you have a dipole moment, as it's called. It's a polar molecule. A polar molecule has, letter D, but the letter H has a dipole moment. Okay, that's what that arrow there represents, going from the partial positive to the partial negative. It has two poles, a positive end and a negative end. Okay, so it's a dipole, or it has a dipole moment. It is a dipole. That's how we say that. Okay, either it has a dipole moment, or it is a dipole, or it is polar. That's another way to say it. Okay. Similarly, CH2Cl2, dichloromethane, or methylene chloride. That's CCl, Cl, H. This also has a broken symmetry, okay, because you got bond like that, and so it has an overall dipole moment that looks like that. Okay, so that's a polar molecule. CHCl3, trichloromethane, or chloroform, CCl, Cl, Cl, H. Once again, you have broken symmetry, so you have a dipole moment. It's kind of hard to see. It's coming out toward us, and it's another polar molecule. And then CCl4, tetrachloromethane, is just C and then 4 chlorines. Okay. And now all the bonds are once again the same. It's a nonpolar molecule. Highly symmetrical. There's no broken symmetry there. All right. So that is a lot of information to take in a single lesson. Okay, but you have your geometries, your electron domain geometries, and your molecular geometries, and then you have your extended geometries, and then you have to consider resonance. Oh, resonance. One last thing. Okay, let's look at carbonate. Okay, CO3 2-. Okay, it has this structure. And we also know that it has resonance. You have to be careful of resonance because you might be tempted to think that this bond is bigger, okay, than 120 degrees. It is not because, that bond angle is 120 degrees. But it's not because all of these are 1 1/3 bonds. The bonds are all exactly the same. Okay, so they all take up the same amount of space. And as a result, this is a nice, highly symmetrical trigonal planar molecule. Okay. So there would be like no polarity there. Okay. So nice, symmetrical, trigonal planar, because the bonds are all exactly the same. That's what resonance does for you. Resonance similarizes bonds. Resonance makes bonds the same. So they take up the same amount of space around the molecule. Okay. So carbonate still has a lot of symmetry. Now carbonite, COO, also has resonance, but it still has the broken symmetry because of the non-bonding pair. Okay. So resonance won't save it there, won't make it nice and symmetrical. All right. But still, resonance, symmetry, geometry, there's a lot to take in there. And practice, super duper important. All right. And that is it for this section, for this chapter, for this unit. I will see you for the test.